Hey everybody, welcome back to the class. I wanted to make this video to go over the answers to the case study number 2. I just finished grading everyone's work and the scores are now posted on Blackboard. There were some common issues that came up with some of the answers. I wanted to go over what the correct answers were. And a few things I'll mention before we get started. When I first posted this, I've mentioned multiple times that you should not wait until the last minute because some things will take a little bit more time than others. And I saw that more than a few times. If you waited until Friday afternoon to even start the assignment, you probably didn't do as well as you had expected. There were some questions that took extra research. There were some questions that took a little bit more time to fully understand what's going on. A few other things that came up. If you've just opened up the assignment and went right to the questions, probably made the assignment a lot more difficult than it should have been, because there was a lot of important information and some important clues given to you in these background paragraphs before the questions even started. And I'll kind of point those out as we go through them. And probably the last big thing that came up, people not reading the questions carefully or answering questions that weren't even asked. That came up more than a few times, where people supplied to me answers that weren't addressing what that specific question was asking at all. So again, it's like anything else that we've done in this course. It's important that you read the questions carefully, and you read the directions carefully. For the questions that had more than one question to them, if you didn't address each question, then you didn't get full credit. Alright, so here's the beginning background information on our patient, Jamie. So again, if you just went right from here right to question number 1, then you're missing out on some important information. For example, this part here, ventilation rate would double his normal rate, but still struggling to catch his breath. Of course, it mentions COVID-19, which was the whole reason why I wanted to use this kind of case study rather than one I originally had planned. So you have some important background information here. Then, of course, you have a data table here. Whenever you have any kind of table like this, that's probably a good clue that a lot of the questions will originate in some way from the data on that table. And almost every question in this assignment comes from this data that's here. So any table like this where you have one column is the normal range for some tests and then the patient's results, always take a look at that, because just by knowing what is normal, you should get a clue on what's potentially going on with this patient. And for those of you that are planning to go on to the nursing program, you will see a chart very similar to this many, many times throughout your education and throughout your career. This is an arterial blood gas lab result. These values that are here, probably a good idea to commit those to memory sooner than later, because these values will come up over and over and over again. And it's the information that's on this table is referenced in question number 1. Question 1 was probably the most straightforward and the easiest one. Just identify the abnormalities in the ABG results and list how they're different. So for pH, normal range, something we've already discussed in our class, 7.35 to 7.45. Jamie's results was slightly reduced, 7.32. Partial pressure for oxygen normally should be between 75 to 100 millimeters of mercury. His is dramatically lower at 55. Partial pressure for carbon dioxide should be between 35 to 45 millimeters of mercury. Jamie's was 54, significantly higher than what it should be. The concentration of bicarbonate, that's what those brackets mean. It indicates concentration of the compound within those brackets. Concentration of bicarbonate ion should be between 22 to 26 milliequivalents per liter. Jamie's was 27, slightly elevated. And then oxygen saturation should be between 95 to 100%. His was 88, which was slightly lower. Now, a couple things I'll mention about this data table. Whenever you see a value that's way too high or way too low, that should immediately draw your attention. That should really stick out as a big red flag. So whenever you saw this table, that value and that value should have stuck out immediately, because they are so much out of their normal range. Partial pressure for oxygen, way too low. Partial pressure for carbon dioxide is much higher than it should be. Those two should stick out immediately. And something else that I'll mention now, because this came up for question number 1. Whenever you see a range that's given, that's the only parameters that you have for that range. the handful of people that said, well, the pH was about normal or almost normal, that is not true. The range is 7.35 to 7.45. Any value outside of that is considered abnormal. It may be slightly reduced or slightly elevated, but that's still abnormal. You cannot say 7.32 is within the normal range because it is not. Same thing with oxygen saturation. This came up a few times. 88% is not considered normal. That range should be 95% to 100%. Anything beyond that range is abnormal. 88 is not close to 95. So these ranges are established for a reason. So just because it's almost there and kind of close to it doesn't mean that it falls within that range. It has to be within those values only. So if you said something like that, you did not get full credit because that's not an accurate statement. So like I mentioned before, question 1 is just identifying what these values are. Are they higher than normal? Are they lower than normal? All right, we'll go on to question number 2. Now when you first read question number 2, I imagine most people got a little panicked, a little bit nervous, because you're seeing names that you haven't seen before, you're seeing equations that you haven't seen before. But this is a good example of a question being very detailed with its background information, but the question that it ends up asking you could be answered without any of the background information that it just gave you. For example, we never talked about Le Chatelier's principle, we never talked about the Henderson-Hasselbalch equation. Those are legitimate equations, and if you take chemistry, especially biochemistry, you'll probably get into those more often. But this equation here is something that we have already talked about in our class. It wasn't presented to you in this way, but we have talked about this. So what this is, carbon dioxide plus water gets catalyzed or gets sped up by the Ca, carbonic anhydrase, to create carbonic acid. Carbonic acid will break down to hydrogen ion and bicarbonate. So this process we've already discussed here in chapter 26 when we talked about the excretion of carbon dioxide. So it gets mentioned here. Cells produce carbon dioxide, it combines with water to form carbonic acid, it breaks down and releases hydrogen ions. Also referenced here in this flowchart. That is exactly the same thing as what's going on in this equation. This is just showing it to you in an equilibrium equation. So the question that number 2 is asking you is, how would you explain Jamie's pH value given his partial pressure of carbon dioxide from table number 1? So you go back to table number 1 and you see that his value is much higher than what it should be. So the amount of carbon dioxide is building up. Well, going back to here, more carbon dioxide means more of a chance to combine with water, which means more carbonic acid, which means more of that can break down to release more hydrogen ions. Well, when you release these, that means you are releasing an ion that is going to lower the blood pH and make the blood more acidic. And you see that in the results here. This is more acidic than what it should be. So all of this information that's here, each value on its own is important, but it's also important based on how they interact with everything else. So when you are learning how to interpret arterial blood gases, just by looking at a table like this, you should be able to tell if the person is going through acidosis or alkalosis. Is it metabolic or is it respiratory in nature? And also, is there compensation? And if there is it partial or is it full? And that could be determined just by looking at the table and knowing what specific values to look at. So that's what I was looking for number 2. The fact that carbon dioxide is building up, which means more carbonic acid, more hydrogen ion be produced, which will lower the blood pH. So anything related to that, you got credit. All right, going on to number 3. See what can you infer about Jamie's bicarbonate concentration level based on blood pH and the PaCO2. And then the second question, which organ system is primarily responsible for regulating bicarbonate levels? We'll answer that part first, because I think almost everyone got this one right. It is the kidneys specifically, or if you put the urinary system, I give you credit because that's technically still correct. So if that's the only part of this question that you answered, you didn't get full credit. There are 2 separate questions here. You have to address both of them. And for many people who try to address the first part, you gave me answers that weren't related to what was asked. You can't just repeat what you put in question 1 saying, well, this level is elevated and this level is elevated, and leave it at that. When it says what can you infer about it, you have to explain what it means. Now going back to look at the results in table number 1, the concentration of bicarbonate ion, yes, it's elevated, but that doesn't really explain anything about the acidic blood pH. What that does explain is there's a compensatory mechanism that's being done by the kidneys to fix that blood pH from getting too low. A lot of people address that concept without using the word compensate. A lot of people put things like balance out or to equal out or to negate the effect of. But that's what that term compensation means. That's what gets asked in question number 4. All right, question number 4 has a acid-base nonogram, and all that means is it's a table that has 3 or more variables on it at the same time. So for this figure, we have arterial blood pH, you have bicarbonate concentration over here, and also hydrogen ion concentration up here. So 3 variables on one table. So I'm going to pull this image out separately. All right, so for question number 4, based on the lab results, which of the following best describes his acid-base status? So I imagine almost all of you did this when you got to this question. You saw where you could match up 2 of the variables that are listed here and then see where they met up and then see which of these categories it fell under. So we'll start with the blood pH was 7.32, which should be right about here. So if you extend that line up, then we had bicarbonate concentration, which was 27. So that'll be right about here. So see where they meet. That would be here where it says acute respiratory acidosis, which is true, but that listing is not in your answers. So you have to figure out what does that mean when it says uncompensated versus partially. But because it is acute respiratory acidosis, you can rule out anything that's metabolic. So A and B are now out of the question. So now your only real question is he going through uncompensated or partially compensated respiratory acidosis? And if you look at this chart, you see a combination of 2 things. You see, other than alkalosis and acidosis, you can see how it may be metabolic in nature or it may be respiratory in nature. So when you talk about compensation, what that means in general is when there's a problem with one of those mechanisms, the other one will try to fix it. It will try to compensate or balance it out. So that's what that term references. And by knowing how to read the arterial blood gas table, you can tell just by that information what's going on. So I'll jump to this image here. Now if you do a search for arterial blood gas interpretation, there are many versions of this table that show how pH and carbon dioxide and bicarbonate, how you interpret these. This is probably one of the cleaner charts that I found that I wanted to use. All right, so we know we're talking about respiratory acidosis. And based on the options that we had in the question, it's either going to be partially or uncompensated. So we won't even bother looking at this third column here. So for both of them, the pH is lower than normal, which is true. For both of them, the carbon dioxide values are going up, which is true. The only difference here is the level for bicarbonate. If there was no compensation, that level would be normal. Well, it's not normal for Jamie. His is elevated. So that means it's going to be partially compensated respiratory acidosis. So your answer for this one should have been D, partially compensated respiratory acidosis. And then going back to our table, his pH is lower than it should be. Carbon dioxide higher than it should be. Also bicarbonate is higher than it should be. Yes, it's only one value higher than that range, but it's still elevated. You can't say, well, it's almost normal. Really important to understand that concept. If it's not in this stated range, it is abnormal. It's elevated or it's reduced. That is important to understand. So because of all those factors fit, pH is lower, carbon dioxide higher, bicarbonate higher. All of that references partially compensated respiratory acidosis. Again, before we go to question 5, we have some background information, some very important information that's listed in here. And actually, the answer to question number 5 is listed in this paragraph. Well, question 5 is reference to these 2 radiographs, what a healthy radiograph should look like and what Jamie's looks like. And you can tell just by looking at them, that is nowhere near how it should look. This is nice and clear. That is very cloudy. Going to the question, based on the changes in the alveolar environment, ARDS, the acute respiratory distress syndrome, explain how the body's response to COVID-19 can cause this abnormal radiograph. So basically, what complications does Jamie have that's causing this radiograph when it should be this? Now, it's mentioned here in the question, healthy air-filled lungs have extremely thin alveolar membranes that appear dark in a radiograph. So because the alveoli are so thin, the light from the radiograph should go right through it. When you're taking pictures of lungs, you shouldn't see anything. You should see just the lung tissue itself, like this. When you get something like this, there's something there causing that opacity to show up. There's something causing that shadow to be made. And you don't want something to be in your lungs when there's nothing that should be in your lungs. And the answer to that question is actually given to you in the paragraph right above it, up here. ARDS is characterized by rapid onset of inflammation and the accumulation of protein-rich fluid and cellular debris. That debris that's being leaked out from the alveoli is causing the buildup of that fluid, which is what you see in this radiograph here. So the answer was given to you, both in the preceding paragraph and within the question itself. So that's what I was looking for in number 5. Question number 6, you're given the equation to actually calculate the rate of diffusion, and you're also given a series of variables here. And this question, when you first look at it, gives you the impression that it's going to be really difficult, really demanding. But this one was probably one of the easier questions, or should have been one of the easier questions. If this were a math-related question where you had to calculate one of these variables or calculate diffusion, that would be something totally different. But that's not what's being asked here. All you're being asked for question number 6 is explain how his complications will affect gas exchange and to identify the variables that are likely to change. So that's all that I was looking for question number 6. Picking out a variable in this equation and explaining why that would give you a radiograph like Jamie's in the preceding question. Something like, well, the thickness of the alveoli is going to be much thicker than normal. That's going to cause more debris to be produced. The area of the alveoli that's available for diffusion is going to be reduced because they are damaged and most likely collapsed. So this just picking out a few of these variables and explaining how that's going to affect the exchange of gases within Jamie and how that's going to give you a much more turbid radiograph like this compared to something clear like this. Going on to question number 7, we have a little bit of background first, then we have some math to do. Again, like we saw with a previous question, the information that's in here gives you a clue on how to answer a following question. And more specifically is this value here, which comes up a few times. But for question number 7, using the following equation, calculate the partial pressure of inspired oxygen for the fractions in the table below. And then you're given information that you absolutely have to solve the equation. Assume sea level atmospheric pressure, or 1 atmosphere, 760 millimeters of mercury. And the partial pressure for normal humidified inspired air is 47. So here's the equation. Partial pressure for oxygen is going to equal the fraction of inspired oxygen times normal atmospheric pressure minus the partial pressure of water. And then you're going to find that value for these 4 values here. So I'll walk you through each of those. And this one was actually not as difficult as some people made it out to be. So the first value you were given was 0.21. When you plug that in into the equation that you're given, 0.21 times the barometric pressure, 760, minus pressure for water, 47. You have to do this part first. Remember your order of operations. If you just go here, going to the right, you're going to get a value that's nowhere near what it should be. So your answer that you should have entered for blank letter number A was 149.73. Now I went back through and checked everyone's work and all the data that was entered. Some people left it like this. Some people added the unit after that. Some people rounded up. Some people only put 1 decimal. I went back through and made sure that everyone got the credit that they deserved. So for the second one, the value was 0.45. Exactly the same thing here. This part doesn't change. The only part that changes is what do you multiply it by. 760 minus 47 times 0.45, 320.85. Next one, a 0.60. Again, that doesn't change. That times 0.60, 427.8. If you put 80, of course you got credit. And the last one, same thing here. That part doesn't change in any of them. Times 1, 713. So that's all that question was asking. Here are the values to find. Here's the equation to plug them into. And probably the only difficult thing that people probably ran into was the order of operations doing that correctly. All right, so going on to question number 8. This actually references an equation from earlier. It also mentions Henry's law. This is a gas law that states the amount of dissolved gas in a liquid is proportional to the partial pressure above that liquid. So if you apply that concept to the diffusion equation we got from part 2, how would increasing the fraction of inspired oxygen, that FiO2, how would that improve Jamie's arterial blood gas levels? So if you, say, follow this pattern here, if you increase these values, how would that help out Jamie? Now there are 2 ways you could have done this question. The more difficult way is to reference the diffusion equation part by part, variable by variable, or to explain how it could help the arterial blood gases. But the easiest way is really just common sense if you think about this logically. The FiO2, that's the fraction of inspired oxygen. Normally, regular atmospheric air, that value is going to be 0.21. That's given to you here and in the paragraph right before this set of questions. So if you have more air available to you to breathe in, well, that's going to increase the amount of air available in the alveoli. That's the whole point of giving supplemental oxygen to a patient, either through a cannula or through a mask. More oxygen present means more oxygen is going to be entering the alveoli to be used. So that's what I was going for question number 8. So as you increase these values, the more benefit Jamie would get because there's going to be more oxygen present in the alveoli. All right, question number 9. This question seemed to be the most challenging one out of all the 10 because this question gave me the most variety of answers, and there were many answers that didn't address the question that was being asked. Are you given some background information first, which is important? And ARDS is classified by the ground glass opacities that are seen in Jamie's radiograph and a ratio of partial pressure of oxygen to the fraction of inspired air, and that ratio is less than 200 millimeters of mercury. This ratio allows for the assessment of blood oxygenation in the presence of supplemental oxygen treatment. So there are multiple questions here. The first one, based on the blood gas values in table 1, what was Jamie's PaO2 to F1O2 ratio upon arriving at the emergency department? And the second question is, what would that ratio be for a regular healthy person? And then how did Jamie's initial ratio compare to that of normal person? So you have 3 separate questions here. All right, so to get full credit for this one, you had to address each of the 3 questions, and I'll show you the easiest way to understand what's going on for question number 9. So all you really have to do for question number 9 is to plug in values for this equation, both for Jamie and for a healthy person, and to compare them. And the values for each of these values, or each of these variables, is given to you throughout the assignment. The first one, the PaO2, that's given to you in table number 1, this value. And the value for the fraction of inspired oxygen is given to you both here and in here. So you have all the values that you need. You just have to know how to use them properly. So for when Jamie first gets to the emergency department, PaO2 was 55. Again, given to you from the table. Divide that by 0.21. So his value will be 261.9 millimeters of mercury. Now the table also gave you a range of what a normal person's PaO2 should be. And that range was between 75 to 100 millimeters of mercury. So I'll give you examples on either of those ends of that range to show you that the answer is still going to be the same. So at the higher end of this range, this ratio, 100 divided by 0.21, 476.19. And on the lower end of that still healthy person at 75 divided by 0.21, 357.14. In each of these examples, this ratio is much higher than Jamie's. So that's the whole point of question number 9. And it's something, if you think about it logically, does make sense. The fact that he's breathing much faster, but is still having labored breathing. There's a buildup of carbon dioxide. There's a reduced amount of oxygen. The pH of his blood is going down, becoming more acidic. So he's losing functionality of his lung tissue. You can see that in the radiograph. You can see all those opacities that are there. that stuff is interfering with how the alveoli can work. If they aren't working properly, the oxygen and carbon dioxide won't be able to be exchanged properly. So that's what I was going for question number 9. So I wanted values for Jamie's ratio when he first got to the ED, and for a normal healthy person, what their value would be and how those two values compare to one another. And Jamie's is going to be much lower compared to a healthy person, which is what you would expect with someone with lung damage like this. And for the last question, number 10, it gives you some background first on two different methods. And this information talks about PEEP, positive end expiratory pressure. It also mentions a high frequency ventilation. And question number 10 is, how can these two methods prevent VILI, which is ventilator-induced lung injury? So there's any number of possible answers here. As long as you mention something about how if you use PEEP, that will lead to less collapsing of the alveoli, which means they can function more efficiently. Or when you mention high frequency ventilation, if you said something about how by doing this you can lower the tidal volume within the lungs, which will help keep the alveoli inflated more often, which will reduce the stress of them inflating, which will decrease the amount of lung tissue damage. But you had to address both mechanisms that were given to you in the question. And you could find a lot of information that addressed both of those concepts in the paragraphs right above question number 10. But if you didn't address both of them, you did not get full credit. All right, I hope this helps with the questions you may have about this case study. I know it was a little bit more challenging than you may have been expecting, but I would not have assigned it to you if I didn't think that you could handle it. And many of you did really, really well on the assignment. So overall, I was very pleased on how this case study went. But if you do have any questions about these specific ones beyond what I covered here in the video, please feel free to email me or send me a text, and I can go over it in more detail if I need to. Thank you for watching.